All right, so you didn't think we'd get out of these energy problems without any energy bar charts, I'm sure. You're probably waiting for them. So here is one. So we've got a solid disk initially rolling without slipping along a flat level surface, and then it's going to go up an incline, yay, coming to rest momentarily as shown. Then it asks you to complete the qualitative energy bar chart shown for the system between the disk and the Earth as it's rolling up and then momentarily coming to zero. It says to put the h equals 0 at the height of the center of the hoop when it's rolling on the horizontal surface. So this is h equals 0. And then our height over here is going to be something above 0. Okay, so it gives us an initial translational kinetic energy value to kind of work from. We need to figure out first if this thing is rolling, it's got translational kinetic energy. We know that because it's got a velocity, a translational velocity. We need to know how much rotational kinetic energy it has relative to its initial translational. So we know that translational kinetic energy is 1/2 mv squared. We also know that rotational kinetic energy is 1/2 I omega squared, right? Everybody's good with that, I hope. And it says that it's a solid disk. So again, we can just go back and look and we can see that a solid disk is 1/2 mr squared. It's right here. So go ahead and throw that in there. Then we can say that this right here, we can actually, I'll just rewrite it, is 1/2 times 1/2 mr squared times omega squared. Okay, so far so good, hopefully. Um, and I'm trying to figure out a relationship, really what my goal is. I probably should have said this earlier. Trying to figure out a relationship between the translational and the rotational to figure out how big the bar for the rotational should be. So I'm going to keep cruising here and see what I can figure out. So we don't know the radius, but just like on the last problem, we have a relationship between radius and the translational and rotational velocities. Remember, we said last time that r was equal to v over omega. So instead of writing r, I'm going to write v over omega. So I'm going to go ahead and write this. I'm going to put those 1/2s together because I can. M times, so this is v over, so v squared over omega squared times omega squared. And again, you see those omega squareds canceling out. And oops, I am trying to go way too fast. I apologize. That should be a 1/4, shouldn't it? Yep, 1/2 times 1/2 gives you 1/4. So now I can say, I'm going to write this down here in a nice way here, that the rotational kinetic energy is 1/4 mv squared. And now we've got a really nice relationship because we see that translational is 1/2 mv squared. Oh my gosh, what is going on, friends? I'm so used to writing 1/2. Please excuse me and my sleepy brain. I apologize. Okay. That rotational is 1/4 mv squared. So however big our translational kinetic energy is, rotational needs to be half as large. So I'm going to go ahead and right because the translational was 4 bars big, so that means rotational is going to be 2 bars big. Now, if we take a look here at the beginning, we know that gravitational potential energy is at 0 because it is at h equals 0, and there is no spring. So I think that we can all agree that there is no spring energy at all. In this case, no outside forces are acting, right? The only things that are acting are the rotation itself that's already started and the gravity that is happening um, and that's the Earth, and it says the Earth disk system. So that means that there's no outside work. At the very top, it says that it's momentarily stopped, which means there is no translational and there is no rotational. And so, friends, we've got 1, 2, 3, 4, 5, 6 bars here. Conservation of energy states then that we should have 6 bars at the end, and they are all in gravitational potential. So there's 1, 2, 3, 4, 5, 6. So your chart should look something like